My name's Leo Orshansky. I'm a second-year PhD student at Columbia University. I'm advised by Henry Yuan and Tal Malkin, and I'm excited to be here talking about our recent work called Private Proofs of When and Where, which is going to be about something called zero-knowledge position verification. All right, so to get started, this is a joint work with, like I said, my two advisors at Columbia, Tal Malkin and Henry Yuan, as well as our postdoc Uma, and from MIT, but who were at UC Berkeley when we started, Shafi Goldwasser and Greg Gluch. So to give a little teaser for what I'm going to talk about, so there's a problem called position verification, and position verification allows you to prove your instantaneous position. So, i.e., you can prove the statement, I am in location XYZ right now. In zero knowledge position verification, we can try proving many other types of statements. Like, for example, I am either in New York or Sydney, or I was not near location XYZ at any time today or yesterday, for which, you know, is essentially the same thing as taking what was previously a predicate over a single point to now a predicate over a general space-time region of points. And we add this in terms of a privacy constraint. So previously, the prover's location was like a public thing that the position verification protocol required to be known to everyone. But now we ensure that it's totally hidden from honest verifiers. So I'm going to start by giving a little background on the problem of position verification, and especially why is it something that quantum researchers care about. So position verification, you know, when I say this, I essentially just want you to think of GPS. Like, we take 4 satellites in 3-dimensional space. We need 4 satellites, and they will send signals all to the same point, and the signals travel at light speed. And by timing these signals and by taking into account, you know, general relativity and things like that, you can localize a point by seeing how fast it takes the point to respond. And here we imagine that the verifiers are trusted, but that the prover is untrusted. So the prover may be trying to spoof its location. And actually, in general, we want security against potentially a number of cheating provers that are all colluding with each other to pretend to be a single prover in some hard to access location. Like, say, you know, a military base contains you know, a high level of security, and we want to authenticate that someone truly is inside of the military base and not, say, 10 people lined up outside of the military base. And it turns out this is somewhat hard to achieve soundness against these arbitrary prover coalitions, and I'll get more into that. But one thing I want to mention is that this is like sort of a rich space in cryptography called position-based cryptography. So if you have this kind of secure positioning scheme, you can turn it into something called position-based authentication. So from the military base, somebody wants to authenticate a command, say, you know, launch the weapon, and we want to ensure that this message only could have come from within the base. So the signature of the message is sort of tied to the location. It's not actually tied to some other kind of public or private key. We really want the credential for this cryptography to be the location itself. And similarly, we have something called position-based key agreement that can be built from position verification as well. And this is when we want the communication to go in the other way. So the verifiers want to encrypt a message that should only be opened by someone who's in the secure location. So if, you know, if 2 military bases want to communicate with one another, they can establish a shared secret key, again, without relying on any other kind of public key infrastructure, but only relying on the fact that the locations themselves are a credential of, you know, someone's identity. And yeah, just to go over some more sort of applications, like, again, we have this authentication encryption for secure facilities. There's another one that's been a popular topic recently, which is that, say, one country wants to manufacture a device and wants it only to be used within the borders of that country. You know, say, you know, GPUs are, you know, scarce resource right now, and it could be the case that one country doesn't want to export its GPUs to another country for them to be used there. And then maybe a third case is that we have all these AI generated articles, fake news, fake videos, etc. What if we could have a digital signature that verifies where a piece of content came from? This could, help authenticity of journalism, let's say. So I'm going to give an example of how position verification works now. This is going to be a sort of diagram format that keeps recurring throughout the talk, so I'll just explain it. We're going to imagine that everything is happening on one line in space. So it's one-dimensional space, and this line is depicted only on the x-axis. The y-axis is going to be time. So, messages and other things will flow vertically. So, okay, we're going to have two verifiers who are on opposite ends of the line send challenge messages to the prover. This is in general how position verification is going to work. So again, this like triangulation type of idea. We're going to have messages from the verifiers to the prover at light speed. We're also going to imagine that the prover can compute instantaneously. So there's no delay that happens when the prover needs to compute. And of course, this is an idealistic assumption, but it turns out the problem is already non-trivial with these assumptions, so we're going to keep them for now. We're also going to assume everyone has synchronized and perfectly real-time clocks, and everyone is exactly where they think they are in space, and everyone can aim their messages exactly where they want to in space. So the protocol is going to be something like the prover gets two unknown challenges from the verifiers and computes some response. So there's some maybe like hard predicate like inner product of x and y that it's going to compute instantaneously and respond back. So this is in fact a perfectly good position verification protocol if we assume that there can only be one spoofing prover. So in the case where the prover is in a different location, we will catch that. If it's in the correct location, it will succeed. And this seems pretty good, except that maybe we have two cheating provers, like I said, that are sort of like surrounding the secure location. And here we have a problem because they can simply copy the challenge that they got and forward it to the other cheating prover. And at this point, they have sort of recreated the state that the honest prover. So the honest prover here would be in the middle, but instead they've recreated its state at two different locations, slightly later, but they can still respond just in time. So this is an attack that successfully spoofs this position verification scheme with just two cheating provers. And it turns out actually the theorem on the right-hand side here is that every such classical protocol, not just this particular protocol, can be spoofed by an attack similar to this. So here is hence why it's a quantum problem. Can
I quickly ask? I think
yes.
So this previous proof, I guess, also works for like do computational assumptions change the impossibility proof, or is it essentially the same?
Yeah, good question. It is for any classical protocol. So yeah, there are any assumptions that you can have computationally will not allow you to do any better. Even in like, say, the random oracle model with purely classical information, there's always an attack. So the quantum model is not the only model that people have considered where you can get around this impossibility, and I'll go over some other models in a bit. But the most interesting for quantum researchers is probably the quantum model. And so we're going to circumvent this attack just essentially by invoking unclonability. So here now the honest protocol is going to be that the prover does not just get x and y, it also gets a state psi, which is just a BB84 state. This protocol is called FBB84. And the pseudocode is sort of on the right, but essentially all that's happening here is that the prover will measure in the basis corresponding to some f of x and y, and it gets a measurement outcome. that it then forwards to the verifiers. The BB84 state was prepared specifically to have, the measurement outcome be when it was measured in basis f of xy. So this protocol is perfectly complete. And it turns out that this attack, pretty much fails with overwhelming probability. And in fact, it can be proven that this protocol is sort of like, information theoretically, in quotes, because, so this protocol is secure against any Alice and Bob that share less than log n entangled qubits. So we're working now in a model where our assumption on the provers is not that they're computationally bounded, but that they cannot build up entangled states between themselves that are too large. So in particular, if they share zero entanglement, this protocol it has great security. If they share a logarithmic amount of entanglement, this protocol is also secure. But if we don't know anything beyond that, and actually we don't know anything in the polynomial entanglement regime, and every protocol can be broken with exponentially many entangled, exponentially many EPR pairs shared between Alice and Bob, can be broken in a way that's a non-trivial generalization of the classical impossibility. So there is a sort of spoofing attack in general against any quantum position verification protocol if the attackers are allowed exponentially many EPR pairs. And so the big open question in this sort of subfield of QPV is that can we find a protocol of which is secure against poly or super poly amount of entanglement. So I'll pause here if there are any questions.
Yeah, sorry, in the BB84 protocol, how is this function f chosen? That is this function of inputs x and y?
Yeah, good. It should be so the goal is to choose it so that this attack here, so this picture of Alice and Bob get to exchange one quantum message in parallel, and then they have to arrive at the correct measurement outcome at the end. So there is sort of a complexity theory of these tasks depending on the f, and it relates to the communication complexity of this f. And so a candidate is inner product. This seems to be the most promising.
I see. And
sorry.
Yeah.
Go ahead.
And also just one more thing to clarify related to Atul's earlier question. So these lower bounds, so are they like I guess they're like in the information theoretic setting, right? Like you're saying that. So is there like any hope to, bypass all these lower bounds in the computational setting if we just care about security against QPT provers in this case?
Yeah, good question. There is something. Let's see. I want to see if I will. Yes. Okay. So I'm gonna actually speak a little bit more on that. Okay. To answer your question, I'm going to highlight these two on the right here. So there's the random oracle model. So using a quantum scheme plus the random oracle model, you can get security against like arbitrary, attackers with arbitrary resource states, as long as you care that they make only polynomial many queries to the oracle. So this is one way to get around it. And actually, there's like a really nice result by Lulu and Chen about a protocol that results from assuming sub-exponential LWE and using quantum. You can actually use a sort of proof of quantumness to create a position verification protocol with classical verifiers. So classical communication, classical verifiers, but a quantum prover. Assuming sub-exponentially secure LWE, you can get much better bounds than we know in the information theoretic setting. So it's not secure against exponential entanglement or even large polynomial sized entanglement, but for like a fixed polynomial, you can construct a protocol such that any attackers with less than that polynomial amount of EPR pairs are, cannot break the scheme.
Oh, so you mean that you need to like fix ahead of time, like the power of the adversary, like what polynomial, and then you adjust your protocol based on that. I see.
Yes, so it's it's not asymptotically secure against polynomial, but like you can get a scheme that's, for example, asymptotically secure against n squared or against
Right.
But these are still quite interesting results, because in the information theoretics model, we don't know how to do better than log n. So yeah, and but in fact, we're going to focus on this bounded entanglement model. I mean, not as I'll say later, our zero knowledge position verification is actually going to be agnostic to the model, so we're going to be able to use any of these sort of constructions for our zero knowledge compiler, but we are going to state our results in the bounded entanglement regime. All right. So I also just want to quickly mention. Go ahead.
Sorry, since you're already talking about the models, one quick follow-up would be that, so there's also this bounded storage model, right?
Yes.
Where it restricts. So is it, because of course here it's more about entanglement than storage, but are there any results where somehow in bounded storage one can do better? Yeah. Does it even make sense? I don't know.
Yes. Yeah. So on the left here, yeah. So the bounded, I think technically there's a bounded retrievable model, which is slightly different than the bounded storage model, is one where the verifiers might send their challenges, like some huge challenges, and the honest prover can compute incrementally on these challenges without remembering them, but just getting one bit at a time. It can sort of like compute the correct predicate, but the cheating provers would be forced to remember everything. I think, and like, actually, the first result on position verification was that you can build a secure protocol in this model, like an information theoretically secure protocol, quote unquote, in this model where you assume memory is bounded. But I think there hasn't been a lot of work on extending that result, or really a lot of follow-ups, because I think it's a bit of a non-standard model.
Thank you.
But yeah. Cool. Okay. So I just want to also mention there was a recent experimental result from NIST, which tries to which successfully implemented position verification for the first time. I believe this blue region is everywhere where the prover cannot be, and the yellow region is everywhere where the prover could be, given this like one-dimensional experiment. So I think it's cool. I think there is a lot of interest from a lot of different communities in actually realizing quantum position verification, because, as I said, it has a lot of applications for security. So all right, finally I'll move on to talking about our work. So this is going to be extending position verification to verify more general position verification, more general properties of position, and doing so also privately. So to motivate this, I want to sort of bring to the attention that like privacy is a serious concern. Not only is it obviously, like people are worried about how much data is being compromised and how much everybody knows about each other nowadays. I think in certain contexts, privacy is a deal breaker for the application. So if you have an application like, for example, military, where it's completely senseless to compromise privacy, then the application itself cannot happen unless you have some kind of private primitive for implementing it. So again, like a position verification protocol where the position is just a public parameter cannot be used for an application where location is very sensitive. And in fact, it can be sort of life or death. So one example that we have is how would somebody prove to a judge that, I was, for example, there was a crime that happened in New York. How can I prove to a judge, well, for the entirety of the last month, I was not in New York at any point? Well, one easy way to do this is just to constantly be running GPS in some provable way and constantly be uploading a history of where you are, which would then be able to, then you could show that to a judge and say, well, look, I wasn't there. And in fact, this is like, I guess this is something that happens now in real life. Our phones do constantly track where we are. And then if you are in trouble, you could go ask Apple, and Apple will say, all right, well, I will show you where you were. But again, perhaps this is not suitable. Maybe we're very unsatisfied with this, with having to record our locations all the time and trust somebody with this knowledge of where we are. So if we had a private way to talk about our location, a private way to prove that I wasn't in New York without saying where I actually was, then we could do this application. Some other applications we have are nuclear treaty enforcement. So there's this treaty that really exists that says you cannot have nuclear weapons in Antarctica. Well, how can I prove to you that my nuclear weapons are in Antarctica without telling you where my nuclear weapons are? We could have geo restrictions, like, for example, in the US, there are certain websites or, certain, say, sports gambling you can do in one state, but not in another state. And if we want to have this verification done in a provable way that can't be spoofed, because the spoofing is a big problem, then again, we're going to want to do this without leaking privacy. And Strava posts, if anyone doesn't know, Strava is this exercise social media where you want to show that you did a run of some, distance, but you don't, you'd rather not leak where you were. And this is actually a real thing that happened, that Emmanuel Macron was in trouble because his location was being leaked when his bodyguards went on runs on Strava. And this is an article from a real newspaper about how Strava leaks, is this big serious security risk. But truthfully, it might be useful to prove some property of our position. Like, I moved across, this line in space, or space-time even, but I don't want to tell you where it was. Okay, so finally, we motivate our definition of zero knowledge position verification. I'm going to go over it because it has a few different properties. So we're going to quantify, or we're going to parameterize by a space-time region R. So I'll give some examples of a space-time region, but we're going to have a region R with many allowed points. So given some region R, a prover who's anywhere in R can always pass the protocol, can prove that they are in R. Outside of R, if we have even some big coalition of provers, assuming they share some bounded entanglement, they will fail with high probability to pass the protocol. And finally, we have honest verifier zero knowledge. So against verifiers who are following the protocol faithfully, as long as they are polynomially bounded, they can learn nothing about the prover's position beyond the fact that the prover was in this region R. So, we're going to have maybe more formally a simulator that for any prover in R, you could sort of replicate the transcript that they might have with the verifiers. But also more informally, it's just their position is hidden beyond the fact that they're in R. And our main theorem in the paper is that we can construct this in a black box way from position verification protocols, and also using private key cryptography. So, like, essentially post-quantum one-way functions plus position verification are sufficient for this primitive. So I'm going to say a little bit more about this general space-time region R. So yeah.
Oh, can I ask a quick question about the definition? So, like in for like the soundness, when you say like coalition of provers, do you have like some like fixed number of provers in mind, or do you mean like for any number of provers this property would hold?
Yeah, I mean, so unbounded number. I mean, I think we can consider it sort of like a prover is an algorithm that might have components in different places. They can send messages to each other. You know, we kind of don't distinguish between a prover that's like 10 different parts and a prover that's one part that's very large. I mean, yeah, so we don't care how many provers, we just care that no part of the prover is in R. So yeah, like formally we might say that there are no, formally we might say that it's a quantum circuit with no gates in R.
I see.
Yeah, and R is the space-time region, so I'll clarify that now. So a region, okay, so what is a space-time region? Well, a region of space is clear. A region of space is like just a number of points in space. A region of time is also clear. So like if I were to say that I was in a particular point yesterday, that's like the region of space-time that stretches vertically over all of yesterday over that particular point in space. But more generally, we're just going to consider a region of space-time. So, you know, a set of points in space-time where maybe they have some meaning, maybe it's more abstract, but yeah, essentially it's going to look like this sort of like blob. And the true position is just, we're going to consider it to be one point in the blob. So I want to mention that our definition on the previous slide of zero knowledge position verification does collapse to standard position verification if the region contains a single point. So sort of more precisely, the zero knowledge condition is vacuous if the region is a single point, because to learn that to learn that the verifiers accept is to learn your true position if your region is a single point. But if your region has many points, then the fact that the verifier is accepted does not necessarily tell you anything about the position. So I'm just going to sketch sort of the way that this protocol might look. So there's this, again, this general region R, and completeness says that if you are indeed in R, then there's some way to respond to the verifiers which succeeds, no matter where you are. On the other hand, if you are Alice and Bob who are outside of the region, then there's some way that this doesn't work. And the zero knowledge says no matter where you are in the region, the verifiers see exactly the same view. So okay, I'll go into the construction now, unless there's any questions about the definition. Awesome. Okay, so it's actually, I say this, but I hope you'll believe me at the end. It's actually quite simple to construct zero knowledge position verification, and we think that this is, a good thing, that it's simple. But I'll describe the construction just using sort of a little roadmap here. So first, we assume position verification exists as a black box. So we have some protocol that already succeeds to do secure position verification, which is resistant to spoofing, etc. And we don't care too much about the model. So quantum, bounded storage, random oracle, etc. Then we are going to run position verification and just sort of cryptographically hide the messages that the prover sends to the verifiers. So I'll explain this more, but the prover essentially just commits to all of its responses in a hiding way instead of sending them in the clear. And then finally, once we've done this committing, you just prove that in zero knowledge that there's some opening that will convince the verifiers that the prover's location was in R. So again, okay, I'll start getting more into this. So for anyone who's unfamiliar, I will go ahead.
Since we're speaking at a high level, you, I think, mentioned that this is honest verifier, zero knowledge.
That's right.
So maybe, but from the roadmap, it looks like it should work in general, right? So it's not so immediate at this point.
That's right. So I think I'll leave it for the end, but I do have a slide explaining why we have honest verifier zero knowledge. It's a little bit subtle. But yeah, for now, let's just, whenever I write zero knowledge, I really mean honest verifier zero knowledge, because if the verifiers are not following the protocol, it turns out there's something that they can do, which is pretty hard to defend against.
So when you say that the verifiers are not honest, I suppose you mean not only do they not follow the protocol, but the positions are not what they claim it to be. Is
potentially, but actually, even if their positions are correct,
even then there's
okay. There's essentially an attack. I'll explain more in detail later, but there's essentially an attack where the verifiers can pinpoint certain locations to send messages to, and not send messages to other locations, but the prover can't tell because the prover is only in one of them. And then, yeah, okay.
Thanks.
But good question, yeah. So, all right, I'm gonna quickly go over the definitions of commitments and zero knowledge from cryptography. So, commitments are a primitive in cryptography where Alice sends Bob a message, and we can imagine that it's in an envelope that's locked. So in particular, what this means is that Bob cannot open the envelope, and yet he knows Alice cannot tamper with it. Then Alice sends Bob some secret string that she was holding, which is we'll call the opening or the reveal, and it lets Bob unlock the message and read what was inside. So we call these two security properties hiding and binding. Hiding is that Bob cannot know anything about the message until Alice has given out the reveal, and binding says once Alice has sent the initial commitment, this is it has a fixed opening, and nothing she can do can later change what this opening is. We usually talk about commitments either in the statistical binding computational hiding regime or computational hiding statistical binding. We are going to use commitments which are computationally hiding and statistically binding, which means that hiding is only against a polynomial time Bob, but binding holds no matter how computationally unbounded Alice is. Zero knowledge proofs are a somewhat related thing, which is that Alice wants to prove to Bob, I possess a string X with property P, or sometimes there exists a string X with property P. However, she wants to do this such that Bob, after being convinced that X satisfies P, Bob should know absolutely nothing else about X. So Bob, for example, cannot just output X, but only he should know that it exists. And there's a relationship between zero knowledge proofs and commitments, which is that a protocol for zero knowledge can be constructed for any NP predicate, assuming the existence of cryptographic commitments. So most people are familiar with this, but I'll just briefly give the sketch, which is that there's a NP complete problem called graph 3 coloring. Alice wants to prove to Bob in zero knowledge that there is a valid 3 coloring of a particular graph that's public to both. To do this, Alice sends Bob a commitment to the color of each node. But Bob cannot open all of the commitments, otherwise Bob will know the coloring. So he will randomly pick an edge and tell Alice to reveal its coloring. Alice reveals the coloring of that edge, and Bob just checks that this would correspond to a valid coloring. So in this way, Bob is convinced that there is a valid coloring, but knows nothing else about it. Okay, so the reason that I've given this background is we're actually going to construct zero knowledge position verification from something that we call a position commitment. A position commitment is going to be like a position verification protocol in that there is a prover at a particular point, and it's going to interact with verifiers to prove that it's at this point, but it can delay the verifiers sort of accepting and knowing what the prover's location is until later when it wants to reveal. So it first interacts with the verifiers to create some position commitment, C, and then it can, wait arbitrarily long and then send a reveal later, which will then convince the verifiers that it was at a particular location. We're going to have hiding against honest verifiers, which is just that until the reveal phase, the verifiers learn no information about the prover's location. By the way, I'm using L comma T here to denote a location in space-time, which is like location comma time. We call this a point in space-time or a position or and so they're supposed to have, honest verifiers should have this exact same view, no matter where the prover was. And then the second property, which we're going to have statistical, we're going to have this property hold statistically, and it's called position binding. It's going to be two things. First of all, the commitment is binding. So, okay, sorry. The first one that's listed on the page is actually that the value of the commitment reflects the true position of the prover. So, not beyond just regular binding, we also want the value of the commitment to reflect some statement about reality. So if the prover was not at L comma T, it cannot produce a commitment that opens to L comma T. So this is like essentially the soundness property of position verification, but just in this more general way where we can first commit and then reveal. And then also we require binding, which is just that each commitment has a unique position and the prover cannot change after committing. Okay.
So it seems that position commitments are stronger than position verification, but are they like strictly stronger, or do we even believe we can construct commitments just from the verification alone?
Good. So actually we show in our paper that it's actually not, it's not hard to show that this primitive implies regular commitments. So so in some sense you do need the cryptography, like you need one-way functions. And this is just because there's sort of computational hiding. So yeah, it seems like there's not much you can do to get exactly this primitive from just position verification, but that's not to say that there's not some other, clever way to achieve sort of hiding without requiring this intermediate step. Yeah.
Right. I see. But for instance, do we? Okay, I see what you mean. But for instance, do we believe that, or do we already know that, let's say, position verification plus one-way function imply position commitments? Because for commitments, one-way functions are sufficient, right?
Yes.
So do we?
Yes.
Read that from? I see.
We construct these from position verification plus one-way functions. Yeah.
Okay. That's great. Nice.
Yeah.
I have a sorry, just since we already started asking two questions. One is
Sure.
a very dumb question, so I'll ask that first, which is why is L capital and T small? Is there some reason, or it's just notation?
I believe we've chosen this because L is multidimensional, so L is actually like a three-dimensional vector,
Okay.
and T is just one dimension, scalar. Yeah.
Okay, good. And the other question was, do you think like one could go weaker? Because I guess you could do commitments with weaker things, right? If you have quantum communication.
Good.
But do you think
So
from existing commitment constructions? Or...
So we use classical communication. So like again in our paper we show that this precise primitive here does imply classical commitments. In other words, it also implies one-way functions. But we could weaken the definition of this primitive to have quantum communication, and then potentially you could get this from quantum commitments, which yes are weaker than one-way functions.
Okay, so it's you don't think it's like a black box thingy, like you just substitute your commitment procedure with the one built using communication and things potentially weaker than one-way functions? Is it not that?
I guess I'm not sure. I'm not sure.
Okay,
But
interesting.
good question. Yeah.
Okay, thank you.
Okay. Awesome. So now I guess we will build these, and as I claimed, it's going to be simple. It's not going to be very complicated. So I'll give an example with just 2 points. So this is like, imagine that our region R consists of just 2 points in space-time, P and P tilde. So the statement of the prover is in R is going to be the statement that the prover is either in P or P tilde. So the prover, let's say, is actually at P, but wants to prove that that he is either in P or P tilde, and there's going to be like a fixed time at which he's proving. So it's like 2 individual points in space-time. And in particular, like the time is going to be at this, if you can see my cursor, right? Okay, so yeah, it's going to be at this particular time that he's going to try to prove that he's either in P or P tilde by responding either to this position verification challenge or this position verification challenge. But somehow the verifier should not be able to tell which one he responded to. So what are we going to do? So here he's going to have to answer honestly, but here he must spoof his response somehow. And again, this is the honest prover that is having to do spoofing. So here there's going to be some pair of challenges. There's going to be like a psi. Let's say I folded X into psi just for convenience, but there's going to be like some psi and some Y, and the prover is going to have to do a measurement at this point and output instantaneously some function. But again, the prover can't do this because the prover is not actually there to measure. So we're going to have to spoof this somehow. And the solution is going to just be to wrap these in encryption. So if this is the honest protocol, then the prover can spoof this simply by encrypting a dummy response. Later, the prover gets his honest challenges and encrypts the honest response. And then to complete this, the prover just has to compute the dummy response at the end as well. So in each of these 4 output points, the verifiers just see some encryption. They don't know what it is. So the position commitment protocol is pretty much as simple as just run position verification, and for each point in the region, send a challenge, and the prover will spoof it with an encrypted dummy response. So just to lay this out in like pseudocode, we're going to have this region that potentially contains very many points, and for each of them, simultaneously, the verifiers will send a challenge. So the protocol is not very optimized, and in fact, it's depending on how you asymptotically think of this region, depending on the discretization that you apply. Like, of course, we can't do this for infinitely many continuous valued points, but let's say there's some discretization. This could be a very large amount of points, but we're essentially going to send a challenge to every point, and the prover will also think about every point, and if he is actually there, he will send the encrypted response, and if not, he has to send encrypted dummy responses that match the timing of when that true response would have come in. Then, of course, to reveal it, there's nothing else to do. The prover just says what its secret key is, the verifiers decrypt and check that there's the unique point where honest responses came from. So are there any questions here?
So the scaling is somehow with the area of the region involved? Is that?
Yeah. So in some sense, we can think of it as a constant because, it's like some, like let's say the verifiers are cell towers, and then like the area is just sort of like the space in between the cell towers, and with some discretization. So they apply some kind of like grid on top of the area, and for each point in the grid, they're sending these challenges. So in some sense, it's a constant, but in reality, it could be a pretty large constant. Whereas the security scales not with this, but the size of the challenges themselves.
Security parameter. Oh,
Yeah.
right.
Okay. Cool.
Sorry, just one.
Yep.
I'm sorry. I think I misunderstood something. So you're saying it's independent of the area that is committed, is involved in the procedure.
The security.
The messages that are
The message. So the number of messages, or like the number of even rounds in some sense. There's like a lot of parallel rounds happening, and the number of those scales with the size of the region. But if
Right.
the region might be fixed in some sense,
Okay.
and the sort of like set of feasible regions might be fixed in some sense, and like we just need to commit to every point where the verifier might want to prove that they were, or where the prover might want to prove that they were. And
okay, got it. You're saying the cell size is fixed.
Yeah.
Okay, thanks.
So just to sort of sanity check the two properties, we do get this honest verifier hiding, that no matter where the prover is, all the verifiers see is just this stream of encrypted messages, which we can think of sort of like at each time step they just get some batch of encrypted messages and they don't know anything else. And for binding, we need, again, that there's two properties. We need that like the commitment can only have one value. That's pretty easy, but also that the commitment encodes the true value of where the prover was. So essentially, in other words, in order to spoof the reveal to some other point, the prover must have cheated in some position verification instance. And this is actually not so easy to show. But we do have a reduction from this position commitment game to a black box version of the position verification game. Yeah, I won't go too much into detail, but essentially this reduction needs to consider the fact that the adversary is non-local, and the reduction somehow needs to decrypt the position verification responses that the adversary is outputting without actually knowing the secret key. But that is how we can prove security. So in particular, we do prove that this construction is secure, assuming, again, post-quantum one-way functions and assuming this black box position verification scheme. So now there's a pretty simple step here to get from this position commitment primitive to honest verifier zero knowledge position verification, which is that the prover simply commits to its position. It generates a classical verifier transcript. So it's actually pretty important that this verifier transcript is classical, because we don't have quantum zero knowledge for NP, but I'll take that back. We don't have zero knowledge over general NP properties of quantum states, or this is maybe not so well defined. So instead, we're going to make sure that the commitment transcript is classical, which also means that we are building this from a position verification scheme with classical outputs, which it turns out there is a large literature about FBB84, which is like this scheme I showed in the beginning, where you measure a state and then you just have a classical output. So that generates a classical transcript. And now we, with this classical position, we're going to define in step 2 like this NP language. So the NP language will essentially say there exists a secret key such that if you take this transcript and run the reveal algorithm on this transcript with the secret key, it successfully reveals to a location L, T, which is in R. So for a given R, we have an NP language over verifier transcripts. So to actually do the proof, the verifier sends a transcript to the prover. Again, we trust the this is partly where we get the honest verifier, but it's actually not the primary point of contention for malicious verifiers. But we do trust the verifier. It's going to send its transcript T. The prover will choose this region R and then run a classical zero knowledge proof. We've already assumed one-way functions, so we can just get away with computational zero knowledge and convince the verifiers that their transcript T is in this language. So are there any questions here?
Yeah, maybe just to make sure that I got this right. So when you're referring to like classical output of the position verification, so do you mean like the proof that I'm in a certain location? Is that what you refer by classical output? So in this notation would be the capital T, or sorry.
Okay, let me rewind here. So okay, I hope my slides are working. Okay, so
yeah.
So this FPV84 scheme
Mm-hmm.
has a classical output B.
Right.
It's not drawn here yet, but these messages here are classical messages.
Mm-hmm.
So, oh yeah, here it is. So when I use capital T, I'm talking about the whole transcript of the position commitment scheme, which, if you remember, is the encryptions of all of these. So we have encryption of B, but also encryption of B1, B2, B3 for all of the points where the verifier sent challenges, where the prover might have been. So the capital T is like actually a list of encrypted measurement outcomes or dummy messages.
Okay. I see.
Yes.
But yeah, you remind the fact that this B is classical in order to just require like a zero knowledge just for NP and not for something beyond NP.
Yes. Correct. Yeah, because like we could do encryption over quantum states. Like say we had a quantum output position verification scheme, we could do the same construction with a quantum encryption, but yeah, then it's not clear how to prove in zero knowledge.
And I guess like maybe one further thing. So assume that you would have like quantum output from the zero knowledge, but then your encryption actually takes quantum states as input, but produces like classical ciphertexts. Then that would still be fine to use this, right? Because you are just then testing something about the classical ciphertext.
Well, I don't see how a black box. So if you had some kind of encryption scheme that took quantum plain text and output classical ciphertext, then how could decryption imply?
Yeah. I was just saying in terms of like semantic. I don't know if that actually makes like a lot of sense, but I was just saying, okay, maybe not for like any.
Because I think if in a black box way, I think this wouldn't work because we need some kind of guarantee that like correctness even still holds when you want to check the transcript. But yeah, if like maybe for a given position verification scheme with quantum outputs, there is a suitable scheme like this. Yeah.
Exactly, that's the thing, because you would only care about like certain quantum states are produced, so you'd only care about decrypting those allowed quantum state. So maybe there's like BB4 state or something. So yeah.
That's potentially true. Yeah.
Okay, thanks.
All right, nice. So nearing the end here, I'm just gonna sort of recap our main result. So the formal statement is given these post-quantum one-way functions, or like equivalently given post-quantum private key cryptography, and assuming secure position verification in some model, then our black box compiler gives honest verifier zero knowledge position verification for every finite spacetime region. So finite region here, like we're thinking about like a discretized fixed sort of subset of spacetime. So again, we can upgrade essentially all position verification protocols, no matter the security model. And in the bounded entanglement model, our transformation essentially preserves security up to a factor of 2, which is, even this factor of 2 is just some kind of weird property of our reduction that it doesn't necessarily have to be there. And we didn't prove this in other models, but we believe that this security preservation should also hold. So I will talk a little bit more about this honest verifier thing. So right now we assume verifiers are honest but curious. Why don't we just figure out how to extend this to arbitrary verifiers? Well, we actually give a sketch in our paper that this is potentially impossible. Depending on the precise way that you model your protocol, or your model, like sort of the capabilities of each party, you could say that this is impossible for the following reason. There's a generic attack against zero knowledge. For honest verifiers, we essentially know that any such scheme will have verifiers sending messages to every point, because otherwise an honest prover in a point that doesn't receive any messages from the verifiers pretty much can't do anything. So malicious verifiers might just they might have a guess for where the prover is. Let's say they guess the prover is exactly at L, T. Well, they run the protocol as normal, except that they only sent messages to L, T. Now, if they guessed right and the prover really is in L, T, the prover doesn't know anything they don't know anything is wrong. They only see messages at their own location, so they will respond as usual to the normal protocol, as if the verifiers were also sending messages elsewhere, but the verifiers know exactly where the prover is because no other prover would have spoken, So we call this sort of like the poke in the dark attack on zero knowledge, and it seems that the only way to avoid this is maybe to assume that verifiers can only send broadcast messages and they can never send like a laser beam sort of directional message. This is potentially reasonable to assume about like cell towers, but it's also, I think, reasonable to assume that they behave honestly in general because, for example, if the verifiers are cell towers, then it seems like it would degrade service if the cell towers were constantly doing this like nefarious behavior. And maybe we just want to assume if we don't want to make weird modeling assumptions like the verifiers can only send broadcast messages, then maybe it's simpler to just assume that the verifiers are honest because this is, we think, fairly reasonable. So another future direction here is that we actually, we prove in zero knowledge that the prover was in one of these locations, but actually, like, how do we know who the prover was? Who are we actually proving something about? In particular, I could take the zero knowledge proof and I could give it to my friend, who then proves to you that he was in my location. But what do you actually learn from this? What's stopping me from doing this? So we want to think about like linking identity between multiple proofs of position, or linking it to sort of other cryptographic credentials. This seems like an interesting direction. And finally, as I mentioned, we have a pretty unrealistic scheme for practical considerations. Like the verifiers are sending messages in parallel to every point in space. They also assume that the prover is exactly at one of these points. We assume that all the clocks are synchronized, etc. And these are all, of course, going to need to change before something is implemented in practice. So yeah, these are all sort of future directions. And with that, I think that's it. So any questions?